Welcome, everybody, to Dark Matter in Depth, where we have a host of amazing scientists, engineers, technicians, and people here today to talk to us about dark matter from deep underground at two deep underground science laboratories. So we have the Stawell Underground Physics Laboratory in Australia and the Boulby Underground Laboratory in the UK. And we are joined by some fantastic people. We have got Kim, Sai and Kieran from Australia, and Clara, Johnny, Beth and Emma from the UK. And my name is Lauren. I'll be here for the whole of this morning or this evening, depending on where you are joining us from. And we will be learning all about dark matter today. So I'm going to hand straight over to Johnny, who is going to give us a little introduction to dark matter. So over to you, Johnny. Welcome.
Thank you very much, Lauren. Hello, everybody. I hope you can all hear me okay. I am talking to you from 1.1 kilometers under North Yorkshire. How awesome is that? I hope everyone's having a wonderful dark matter day and a very appropriately spooky Halloween. We're feeling the Halloween spirit here at Boulby. I've drawn on my hat a little bit to celebrate the occasion. So happy Dark Matter Day. I hope everyone's having a great start to the day if you're watching this in the UK, or I hope that everybody's had a great day if you're watching this in Australia. It's very exciting to be able to do a live link like this and talk about dark matter from opposite sides of the planet. We're very, very excited, and we've got a really exciting hour ahead of us. But I'd like to kick things off by talking a little bit about dark matter. And specifically, what is dark matter? Because that's the question, really, isn't it? What is dark matter? We don't know. Nobody knows. And it's one of the big mysteries of modern physics. What is dark matter? Of all the big questions about our universe that we don't know the answer to, what is dark matter is one of the most fascinating. But we know a few things about dark matter. And before we get into that, let's start by dissecting the phrase dark matter, because it sounds mysterious, it sounds scary. But actually, as a phrase, it's quite simple. Dark, in this context, just means invisible. Stuff that we can't see with our own eyes. Stuff that doesn't produce light or reflect light or interact with light in the same way that normal matter does. So dark, invisible. Matter is just the physicsy word for stuff. So dark matter just means invisible stuff out in space that we know is there, but we can't see it. But how do we know it's there? That's a great question. On the subject of questions, actually, I'll quickly say we have got a Q&A feature on this webinar. So if you do have any questions about anything throughout the entirety of this live link, whether it be about dark matter or about the two laboratories that you're going to be seeing today, pop your questions in the Q&A. So how do we know dark matter exists if we can't see it? Great question. The dark matter search revolution kind of kicked off in the late, in the 1960s, when an American astronomer called Vera Rubin was looking at galaxies. More specifically, looking at how quickly do galaxies rotate and how quickly do the stars in the galaxies move. What we expect to see based on our current understanding of physics, or our current understanding of physics for the time, was that stars nearer the center of the galaxies should be orbiting, should be moving a lot faster than stars near the outside of the galaxies. And we see this in our own solar system too, you know. Mercury, it takes a lot less time for Mercury to do a full lap of the sun than it does for Pluto to do a full lap of the sun. And we expected to see the same things when we looked at stars in galaxies. So Vera Rubin and her team looked out in space and looked at our nearest neighboring galaxy, Andromeda. And they saw something that didn't look right. They saw that the stars in Andromeda, near the outside of that galaxy, were moving a lot faster than what they should have been. That's a problem, because that kind of breaks what we know about our universe and how we understand gravity. But okay, sure, maybe Andromeda is just a weird edge case. So Vera Rubin and her team looked at loads and loads of other galaxies out in space. And what they found is that they all did pretty much the exact same thing. All of these galaxies are spinning way faster than what they should be. And this is a big problem, because it means that either our understanding of gravity is wrong, or there's more mass in the universe than what we can actually see. Either way, this totally breaks our view of the universe and what it's made out of. So we know that gluing these galaxies together and causing them to spin much faster than they should, there has to be some invisible stuff holding them together. And this invisible cosmic glue, this invisible cosmic scaffold, is what we call dark matter. It's matter that we know is there because we see its gravitational effects and the way that it affects galaxies, but we can't see it because it's invisible to the human eye. So we have to work out what dark matter is. We know it's there, but we don't know what it actually is. And our current best guess is that it's a type of particle, a new type, a fundamental particle, the very building block of the universe that we have not yet observed. It would be an addition to the standard model, a type of particle that we do not know about currently. And we call these WIMPs, weakly interacting massive particles. There are other theories as to what dark matter could be, but that dark matter is a WIMP is certainly the most popular of the theories. And that leads me on to where I am now, which I'll very quickly say in the last couple minutes that I have, is that we want to try and detect WIMPs. And we can do these in a variety of ways. You'll hear about others later. But one way in which we do this is by running dark matter detectors in deep underground science facilities, much like Boulby Underground Lab, but also Stawell Underground Physics Laboratory in Australia, which you'll hear about very, very shortly. Because if we're trying to look for these really, really rare dark matter particles, these elusive, mysterious dark matter particles that are really hard to look for, by coming a kilometer underground, you filter out a lot of cosmic noise, a lot of cosmic radiation that's prevalent on the surface of the Earth, meaning that you're left with a really low radiation environment down here in our lab, where you can look for those rare dark matter particles without the interference from other particles, from other radiation. Okay, that was a whistle-stop tour of dark matter. I hope that has set us up well for the rest of the live link. So I'm now going to pass you over to, let me just see who I'm passing over to. We're going to do questions on dark matter now for a few minutes. So if anyone's got any questions, pop them in the webinar chat. And if not, we will hand over to the Australian Underground Lab, Stawell Underground Physics Laboratory. Do we have any questions so far?
So we don't have any questions in yet, but we can just give people a moment to type. So somebody has asked, what are the alternative theories to WIMPs? So Johnny, I don't know if you want to answer that or if you want Kieran and Sai to jump in and answer as well.
So I can begin talking a little bit about that, and then anyone else feel free to jump in and add an addition. So some people think that maybe dark matter doesn't exist at all, and that actually we need a modified theory of gravity. So this is a whole other area of research, modified Newtonian dynamics. And this looks at, well, what if dark matter didn't exist, but we just needed a different theory of gravity? But currently the consensus is that dark matter is probably going to be a WIMP. But there are other varieties of dark matter as well. Some people think that it might be something called an axion, which is like a really, really, really lightweight particle. Anyone want to add anything to that?
We have some people at Melbourne University where the supple team works looking at strongly interacting massive particles, which are like a cousin of WIMPs, the weakly interacting massive particles. It's much the same story, but part of what motivates us to be looking for WIMPs is the fact that we know in the early universe it was really hot. There was a lot of dark matter, there was a lot of normal matter, and we imagined that they were bumping into each other all the time, heading between matter and dark matter in something like a chemical reaction, but it's particles exchanging between matter and dark matter. And what we expect is, as the universe cools down, that interaction is going to be happening less and less. And at some point, the dark matter particles and the matter particles are going to be so cold that that interaction can't happen anymore. They can't bump into each other hard enough that matter particles turn into dark matter particles and vice versa. And that's the prediction that brings us to the weakly interacting massive particle. A very similar story can get us to the strongly interacting massive particle, where they don't actually get into Earth at all. And if it were the strongly interacting case, we wouldn't be seeing them in our underground labs. But it's just the gamble that physicists have to take when we're deciding where to look for them.
Amazing, thank you. We've had another question that says, what types of detectors or machines are you using to look for WIMPs? Who would like to answer that question?
I can go for that one if you like. So, and that's, I saw that question in the chat and I've wandered over to the correct part of the lab, especially for this. So I'd like to show you what might be my favorite project personally at Boulby, which is one called NewsG. And NewsG is a dark matter research collaboration looking to design and implement dark matter detectors, spherical dark matter detectors, to specifically look for low mass WIMP candidates. So WIMPs, if dark matter is a WIMP, it could have a variety of masses. And the NewsG collaboration is looking to design detectors specifically to look for lighter weight WIMP candidates. So this is just a small prototype spherical detector that they've got in our lab, and they are currently working to electroform a much larger spherical dark matter detector. But I won't say any more than that because I'm planning to talk about it in the Boulby tour later. So stay tuned.
So I think we've got time for one final question before we head off on a virtual tour. So our next question is, are there any other ways to detect dark matter other than Vera Rubin's quickly spinning galaxies?
I can answer for how the Stawell team is doing it. So for us, what we imagine when we're looking for WIMP dark matter is that there's a dark matter particle that exists like a gas throughout the galaxy, and the Earth is moving through that gas. The Earth and the Sun, the whole solar system, moves through that gas as we spin around the galaxy. And what we think would happen there is while we're moving through it, there's going to be WIMPs going through the Earth, going through all our terrestrial detectors all the time. And us here at Stawell, we have a certain type of crystal sodium iodide that we predict when a WIMP bumps into the crystal, it's going to give that crystal enough energy that it will glow very, very faintly. And if we use super specialized cameras to look at the crystals, we might be able to see that glow. So that's the way that we're looking for dark matter.
So I can add in, so complementary to all of the fantastic research that's going on underground, another way to detect dark matter or to find it is to collide matter particles together and then look for something that's missing. So what's really nice about the research that's taking place underground is that if one of these experiments were to discover a type of WIMP or something, then we would want to try and produce it directly and study it in more detail. So you can either detect it coming in, the dark matter particle coming in, or you can try and use matter to create dark matter and then study it in the production.
Fantastic. Brilliant. So I think that is the time we have for questions right now about dark matter, because it is now time for us to go on our virtual tour of Stawell. So I'm going to hand over to Kieran, Sai and Kim straight away for a virtual tour of Stawell.
Hi, everybody. Welcome to Stawell's Deep Underground Physics Laboratory. We're actually the only deep underground laboratory in the Southern Hemisphere at the moment. And we are a much smaller facility than Boulby and a much newer facility than Boulby. But what we have in our pocket at the moment, and I'm going to turn the camera around so I can show you. It shouldn't be hard, but there we go. How big our cavern is. So you've got Kieran and Sai waving at you down there. And our cavern for our dark matter facility is 12 meters high. So we're 1 kilometer underground and we're inside an operational gold mine called the Stawell Gold Mine here in west of Melbourne in the southeast corner of Australia. I will go to turn back around and I'll go this way as well so you can see everything all at once. So the Stawell Underground Physics Laboratory, we're inside the Stawell Gold Mines. It's about a half-hour drive down through the operational tunnels of the mine for us to get to our facility down here. we've been operational since October 2023, so around about 2 years of operations here at Stawell. And we were built specifically for the Sabre South dark matter experiment, which Sai and Kieran will talk a little bit more about in a minute. So obviously one of the bigger logistical challenges for having an underground laboratory deep underground is getting everything into the facility. So as I said, we've got to go through those operational mining tunnels, and which we share with all of the operational mining trucks, and bring everything into the facility and construct it deep underground in Victoria. The other challenge that we have down here is it's really hot underground. So outside in the mining tunnels, it's 40 degrees at the moment, and it's 95% humidity. And I know many of you probably think we're in Australia and it's like that all the time, but it's actually just a nice spring evening here. So it was probably a lot cooler on the surface. It's probably less than 20 degrees on the surface, which for us poor Australians is really quite cold. Other research that we are either currently doing in the Stawell Underground Physics Laboratory or have aspirations to do, we have a seismometer underground. So you can actually see how earthquakes around the world, how they arrive at Stawell. And we're also doing some radiation biology experiments down here at the moment. And we are aiming to have a material screening facility, which I know Beth is going to run through the Boulby facility that they have there as well. And I'm going to hand over to Kieran and Sai, who can talk to you about some of the equipment that we have installed here at the moment for the Sabre South experiment. Over to you guys.
Hello, everyone. Happy Dark Matter Day. Hope you guys are hoping that everyone's having a wonderful day. I'm just going to share my screen to just give you a brief overview of the reason why we're doing the Sabre South experiment and why we're doing it here. So as Kieran mentioned in the Q&A earlier, we are currently, one of the theories behind dark matter is that we are passing through a wind of dark matter particles. So there is a wind, and we're either going in or out of the wind, as we can see in the picture here, depending on whether the Earth is as the Earth moves around the sun. So, for example, as we go, for example, in December, you can see that we're going out of the wind, and in June we would be going in towards it. So intuitively, you might expect a sort of an oscillating sort of flux of dark matter particles. So the amount of dark matter that hits you should vary, should oscillate in a certain way. And you would expect, if you'd constructed a detector underground, you would expect to see some result that looks like that. And in fact, an experiment in the Northern Hemisphere called Dama Libra, which is located in Gran Sasso in Italy, has measured exactly that. And so what they used is 250 kilograms of sodium iodide crystals, and they took data for over 20 years. And what you can see, their measurements that they took, the measurements that they obtained in the bottom plot in this figure down here. So the general trend is that you should see an oscillating pattern of dark matter, and this seems quite this seems like something you would expect. But the problem is this result could not be replicated in other similar experiments that were based in the Northern Hemisphere, which leads us to think about whether or not this is a seasonal effect or whether there's something else going on here. So in order to understand whether this is a seasonal effect or anything else going on, we built the Sabre South experiment. And this is located in the Stawell Underground Physics Lab, which is where we currently are, 240 kilometers west of Melbourne, as Kim mentioned. And we're located a kilometer underground, as Johnny mentioned, to mitigate the effects of cosmic rays and muons. What we use here are high purity sodium iodide crystals. And as Kieran mentioned, we place them deep underground in these enclosures, as you can see in the figure up here. the top figure is the entire assembled Sabre detector, which is what we're building towards. And what we're trying to do is to see whether a dark matter particle can interact with our crystal and excite the atoms in that crystal and produce some light. That light can be detected by what we call photomultiplier tubes. So you can think of those as little cameras that detect the light. So these are the three sub-detectors that are made up that make up the Sabre experiment. That is the crystal, the set of crystals coupled to the photomultiplier tubes, or the PMTs. We have what's called the LAB, liquid scintillator veto system, which is the huge tank outside here that you can see. And the purpose of that veto is to throw away any events which may not be dark matter. So, and we also have a plastic scintillator muon veto system, which works together with this liquid scintillator system to throw out any events that we're not so interested in. The idea behind those two systems is that if we have if we have hits happening in both the crystal and the veto photomultiplier tubes, we can classify them as background. We don't want them. So now I will throw over to Kieran to see if he has anything else to say about this.
Yeah, do we have time to quickly have a look around Stawell? So unfortunately, we're speaking in the present tense, but the Sabre experiment hasn't been brought down here yet. Otherwise, this room would be full where Sai is. But we do have, if we can see it here, our clean room and glove box. So this clean room, can you see all right? We have our clean room and glove box. This clean room is important for the Sabre South experiment because the whole reason we're underground here is to have as low a radiation environment as possible. And one of the biggest risk factors is us humans bringing our radiation into the clean room if we had banana for lunch or something like that. And we have a Homer Simpson style glove box for being able to handle the crystals. The crystals will be made of sodium iodide, which if we get any of the water from our hands onto the crystals, then they would dissolve and we'd lose the experiment. And we have here our first working part of the experiment, the muon detectors. So muons are a particle that's created in the upper atmosphere 11 kilometers above us right now. When rays from the sun hit the upper atmosphere to create a high energy cascade, these muons are super high energy particles that will come down and on the Earth, in an undergraduate class that I run, we're looking for muons. If you put a muon detector on the Earth's surface, you're seeing them every second. They're everywhere on Earth's surface. But down here, if you had that same muon detector, you'd be lucky to see one in a minute. We've been running these muon detectors for about a year and got a result for the number of muons we see down here. All I can remember is it's not many at all, but that'll be our first published result here in Stawell. But that's about all we have for the Sabre South experiment in Stawell at the moment, and hopefully exciting things to come there.
Fantastic. And I do believe that we've got a couple of questions for you to ask now. So somebody wants to know a little bit about qualifications. So to work at Stawell, what qualifications do people need to come and work at one of at Stawell? And then we can ask Boulby later as well. And do you offer internships to students?
So at the Stawell Underground Physics Laboratory, we operate as a company to run the facility. So as qualifications for working for Stawell itself, then really it's the technical skills to make sure that the facility is operating really well and that the intersection between the mine and the and keeping a clean laboratory works really well. Our researchers who are conducting the experiments down here, well, of course, they've got their very clever and extensive qualifications in science, in physics, in radiation biology, in all sorts of different scientific disciplines. At the Stawell Physics Laboratory, we don't offer any internships at this time, but the Dark Matter Centre is part of the University of Melbourne, and the University of Melbourne does have a work experience program. So you jumped onto their website, then you could probably find more information about work experience at the University of Melbourne and try to connect with the Dark Matter Centre.
Amazing. Thank you so much. So our next question is, how do you avoid neutrinos causing false alarms?
So that's a really good question. Neutrinos are going to be a really big issue in WIMP detectors moving into the future of large-scale WIMP detectors. But for Sabre South, we're actually not sensitive to such low energy interactions. So the neutrino, for anyone who doesn't know, is a tiny particle, the smallest of any particles, and it's constantly whizzing around space at close to the speed of light. And we do have neutrinos coming through the Earth all the time from lots of different places. They come from nuclear reactors in our nuclear power plants. They come from the sun, and they also come from interactions happening in the upper atmosphere. And while they will pass through our detector, they'll impart such a small energy on our crystals that we won't actually be able to see it. So it's not going to be an issue for us. But for the future of dark matter experiments, it's going to be a really big issue. And I think what looks like the best way that people will be able to avoid it in the future is by trying to understand the direction of where particles are coming from. So we know with neutrinos, there's only a couple of places they can come from: the sun, the atmosphere, and nuclear reactors. And if we know what direction all those things are, we know what direction to expect neutrinos to be coming from. And that's one way we'll be able to avoid neutrinos creating false alarms in future experiments.
Amazing. Thank you so much. And I think we've got time for a couple more questions. So we've got a question in about how you get underground. So you mentioned that it's a drive to get to where you are. Does that mean you can kind of come and go as you please to go to the lab, or do you have to come at set times? Tell me more about that.
That actually is the lovely thing about the Stawell Underground Physics Laboratory, that we do come and go to some extent as we please, because obviously as an operational mine, the mine does blasting a couple of times a day as well. So everybody has to be out of the mine and tagged off our tag board whenever they're getting ready to blast. But otherwise, as long as the mine has been cleared from blasting, then we are good to jump in the car at any time and head straight down. And whenever we're ready to go home, we can head back to the surface.
That is very, very cool. So if you forget your lunch, do you eat your lunch down there, or can you nip back to the surface?
Look, it's an hour round trip. So no, we do like to bring our lunch down here for it, not pop up to the cafe for lunch.
Excellent. Fantastic. So I think that is all we have time for on questions so far, but we will definitely come back to see you in a little while. Thank you so much, and we'll get thinking about our next lot of questions for you. But now is time for us to hand over to the team at Boulby. So I think we've got Johnny, and then we've also going to have Beth, Emma, Clara, and Johnny, who is also here. Fantastic. So over to you, Johnny. Take us on a little tour of Boulby.
Yeah, thank you very much, Lauren. So yeah, like Lauren just said, I'm going to spend a few minutes now, just a short few minutes, finishing off the main hall, which is where I started the live link earlier today. This is the main hall of our laboratory. This is the interior lab space, which we keep very, very clean. And this is where we do the majority of our particle physics and particle physics adjacent experiments. And like we've talked about so far today, I'm currently standing in 1,000,000 times less cosmic radiation than what I would be on the surface. So this space here is really important for doing that low background particle physics type of science. And I'd like to just tell you a little bit about a few more projects that we have in this space. Some are dark matter related, some not so much, but I hope you find interesting nonetheless. So I talked a little bit earlier about the NewsG collaboration and this detector that they have with us, this small prototype one, which they're using to test and develop technologies for looking for low mass dark matter candidates, for looking for lightweight WIMPs. And there's a shoot off of this project is what we call electroforming. So NewsG They want to have a bigger version of that detector in our lab, a 2.5 meter diameter, ultra pure copper sphere they're going to use to construct an incredibly sensitive dark matter detector here in our lab. But we have to get a lift underground to get down here at Boulby, which means that it's sometimes hard to get big things down. Everything you see around me, this entire lab, our crane, this massive detector next to me, all of this had to come down in parts and had to be assembled underground because everything has to fit down that lift shaft that we come down in. So in order to get this really pure, really low background, 2.5 meter diameter copper sphere down for this next generation News G detector called Dark Sphere, we're going to need to grow it underground, grow a metal sphere from scratch. And this is what electroforming, this project, is doing. They're testing technologies and testing processes to grow metal from scratch underground here at Boulby so that we can have this next generation detector in our lab, which is very exciting. And then the last thing I'd like to talk about before I hand you over to Beth in Bugs is this space here. This is our large experimental cavern or LEC area. Hang on, let me walk down to the very end so that you can get a better view of it. So this is a larger section of our interior lab space, which we use to hold bigger projects like this one. This is Button. Button is a anti-neutrino technology test project looking to test and implement technologies for future medium and large scale anti-neutrino detectors. It is a very big detector. It's our physically our biggest project. And it's a 30,000 litre steel water tank. It weighs 50 tons when filled with water. And this will be trying to develop and test and implement technologies for future water Cherenkov detectors, which is a type of anti-neutrino detector. So I'll show you one quick picture of what the inside of this detector looks like. It's filled, it's lined with these electronic eyes that look like light bulbs called PMTs, photomultiplier tubes that can detect flashes of light within the detector that tell us that a particle, an anti-neutrino, has passed through. So this is very exciting and very big. I'll hand you over now to Beth. Beth is hopefully in Bugs, and she's going to tell you a little bit about material screening and how that fits into this international game of looking for dark matter. So Beth, over to you.
Thank you, Johnny. That was great. Good morning or good evening, everyone, wherever you're watching. Happy Dark Matter Day. My name is Beth, and I'm in Bugs. This is Bugs, the room I'm in right here, and Bugs stands for Boulby Underground Screening. I am underground with Johnny. I have a different hat on to Johnny because I am in a different lab, separate to the main lab, where Johnny's just given you a quick tour. This is because the main lab is a class 10,000 clean room, whereas the Bugs lab is a class 1,000 clean room. And these numbers, 10,000 and 1,000, refer to how many particles of dust per cubic meter we have in here. So in here, we try and keep it as low as possible because these detectors that we have are very, very sensitive and we don't want any contamination. And I'll explain to you in a bit why that's so important. So as Johnny has explained to you, that coming underground is ideal for scientists to put their dark matter detectors and their rare event particle detectors because we have 1 million times less interference from cosmic rays from the sun. So when they come down here, they can build their detectors and get less background radiation that's going to come in and mess up with their results. So they're building their detectors deep underground. But there is a small problem in that every little material that goes into that detector is going to be a little bit radioactive. Everything is a little bit radioactive. And even the tiniest amounts of radiation can cause a big problem in their detectors. So the solution to that problem is a clean room like this, like Bugs, a screening facility, because we can find out exactly what radionuclides are present and how abundant they are in their materials. So firstly, they can send us the materials that they're thinking of using in their detectors, materials that they might buy in to be ultra pure, low background materials, so they're not releasing much radiation. We can screen them and see exactly how ultra pure they are, so they can determine which ones they want to use. And then when they've found everything they want to use, all the bits of electronics, all the shielding materials, we can screen samples of them and create what's called a like a background radiation model. This is their expected amount of radiation that they're going to have in their detector, and they can subtract that so they can clearly identify a signal that's come from dark matter. So this is something that happens before most of their construction, so that they know exactly what to expect when their detector is made. So the Bugs facility offers different types of radiation screening. We have the XIAs that look for surface alpha contamination. We have our radon emanation facility, our surface ICP-MS, which is a mass spectrometer which tells you over different radionuclides in the decay chains of uranium and thorium. And we have our germanium detectors, which look for ionizing radiation, like gamma rays and X-rays. And we are currently the only screening facility in the world that offers all 4 of them screening techniques. So scientists building their detectors can request different types of screening techniques for their materials to go on, and we can find out how pure these materials are to create their background. So we get scientists sending samples from many different labs, many different projects, Nobel Prize winning projects, the world's current most sensitive dark matter detector, LZ in America. We've screened a lot of stuff for them. And we get to take part in the first steps of these great new projects that are going to make huge strides in science. And that's very exciting to be able to do. I'll quickly tell you a bit about how these germanium detectors work. So you have your germanium detector, put a little sample on top. When it releases radiation, that will interact with the germanium crystal, sending charge carriers to the electrodes, which will produce a voltage that corresponds exactly to the energy of that incoming radionuclide. So we can look at the counts to see how abundant that is, and look at the energy to identify which radionuclide that is. And these are very, very sensitive. We house them in low background lead detectors with an ultra copper liner on the inside to reduce any more radiation getting in. And they have to be extremely cold for them to work. These are cooled with liquid nitrogen that we make ourselves from the very dusty air in the mine, to keep these really, really low background, so we're not getting any more contamination in here. When we're in here, we need to be fully kitted up. If I was changing any samples, I would have masks on, double gloved, everything, to try not to introduce any more dust into that environment. Thank you for listening to my quick tour of Bugs. This is a very exciting place. And it's very exciting to know that we're handling the little bits of electronics in here that could one day be destined to find dark matter. So this is a very, very exciting place. And now I'm going to hand you over to Clara, who's going to explain some of the dark matter searches going on right now at the Large Hadron Collider.
Thanks very much, Beth. And first of all, I want to say thanks so much for inviting me down here. This is my first time in the Boulby Underground Lab, so I'm so excited to get to see what's going on down here. So yeah, my name's Clara and I'm a particle physicist. I work on the ATLAS experiment at CERN. So as I kind of touched upon earlier, we're trying to make dark matter in our collisions in order to be able to study it. But because, as Johnny was saying earlier, dark matter, you know, we don't actually know what it is. There are lots of theories about what it could be, and we see its effect in the universe, but we don't know what it's made of. So we have so many different exciting experiments to be able to understand as much as possible. There are satellites out in space studying the evolution of the universe over time. So for example, the Euclid telescope is out in space studying that. And then we have the experiments here that are studying the sort of direct interaction of dark matter with matter. And then at CERN, we're trying to turn matter into dark matter so that we can study it and see what it does. But this is all assuming that it could be a particle, because as was touched upon in the webinar earlier, it might not be a particle. There are other hypotheses of what this substance is. But we have to share our results. The scientific community is all about collaboration. So we learn from each other from the different experiments. And so that's why I'm so excited to get to come underground today and see what's going on and to join this webinar to learn what the other experiments are doing so that we can then put that back into our own research and be able to learn more about dark matter and hopefully one day be able to explain what this mysterious substance that makes up a big chunk of our universe is actually made of. So we're underground here in this section.
Hi guys, my name is Emma. I'm down here with Clara, and I'm just going to tell you, I work here at Boulby. I've been here for a very long time now, 15 years. And I'm just going to tell you a little bit about the mine and the lab itself. So you've heard an awful lot about dark matter and all of the incredible things that we can do with underground science, as Kim was talking about in Australia. And we want to exploit as much as we can by having this fantastic space underground. So it's not just about dark matter for these underground labs. There's a whole world of science. And one of the interesting things, if I just can lift you up and show you around a little bit here, this is our roadway. I've got it, thanks. And so you can see behind me, this is a mine roadway. This is outside, and we call this our outside experimentation area. And we use this for all kinds of things. We can test Mars rovers. We've trained an astronaut. There's all kinds of incredible things that we can do out here. And that's thanks to the fact that this mine is here already mining for the different minerals. So just so you know, this salt that I'm standing in, this incredible roadway, is made up of these cool salt crystals. So that you can just see one here. This is 250 million year old salt that was left behind by an ancient sea called the Zechstein Sea. It touched on the east coast of the UK here, and it goes right out under Europe. And the reason that this mine is here was to exploit this mineral in the first place. It doesn't look very exciting. It's kind of red when you get up close. You can see the crystals, but this is potassium or potash. And it's used as a fertilizer all around the world. And so this mine started in the late 60s, sinking their first shaft. It took them 2 years to get down to this 1.1 kilometer level in the 60s, and they started mining that potash. About 10 years ago, they found a new mineral, this is called polyhalite, and this is also fertilizer, and it's actually a little bit better than potash in some ways, because this rock, you could take it just as it is there, crunch it up, and put it straight on the soil, and it would be useful fertilizer. Whereas the potassium here, this needs to go and get redissolved to get rid of all the salts and the other stuff that's in there to find the usable product. And so this mine mines now polyhalite, which is actually 200 meters below us in this salt. But the incredible things that this salt has to offer just go far beyond the ability to be able to get rid of ice on the roads or fertilize fields. Because when you take a long, hard look at these crystals, and I'm just going to show you through my lamp here, if I can get the camera to see it. So these crystals, as that seed dissolved away, it left behind these crystals growing. But what actually happens is inside of the crystal structure itself, little bits of that sea get trapped. And so what we've got here is a 250 million year old time capsule, which has little bits of ancient sea trapped inside of it, which is just incredibly cool. And if we can access that, not only can we find out a little bit about what life was like on the surface of the Earth when this was Pangaea and we were about 10 degrees north of the equator, but also if there was any life in this sea. Now, I'm not talking about big life like fish and mammals. We know there wasn't. It was an inland sea. It was very shallow and tepid and very, very, very salty. But what could have lived in here were little bacteria-like things called archaea. These are single-cell microbes. We know they exist on the surface in very salty seas like the Dead Sea, but this sea may have had them. And they will have been trapped in here along with that water, but they will have died. It's 250 million years. The food source will be long gone. But maybe we can find some fossilized remains of DNA or RNA or anything that can tell us a little bit about them. And that's incredible in itself. We've got these little time capsules. But this gets even more interesting when you find out that Mars has salts, just like this. Those salts are billions of years old, and if we can get our hands on these Martian salts, potentially they will also have these little fluid inclusions or other things trapped in the salt crystals that can tell us what Mars was like if it was an ocean planet once upon a time. And so the scientists from NASA and ESA, they get very excited about the prospect of being able to explore this space, this Mars yard as we call it, and we do all kinds of incredible things. You can potentially see from the posters on the wall here, I'll just spin it around. We've got a prototype Mars rover that we had underground. They did loads of scanning and all the kind of things that you expect that would go on a Mars rover, cameras, sensors. We test them all here at Boulby in this extreme environment before they go off to space. Robotic dogs get tested. This isn't so much for space, but looking at extreme environments where humans can't easily get to. We've got geologists and who are looking at the different types of salt and the different areas in the salt to see what has been trapped in there over all that time and has been kind of preserved in these areas to tell us about what life was like, lipids from leaves and all kinds of cool things. Just here behind me, these domes represent a study that's looking at how we can support humans when we send them to Mars. And we know that humans are going to struggle on Mars, especially on the surface. It's very high temperature or very low temperature, depending on the time of day. There's very high radiation and space rocks that are constantly bombarding the surface. So when we go to Mars, it's highly likely we're going to try and put humans underground. There are all tunnels, old lava tubes on Mars. Once you go in there, the temperature is about 17 degrees C all the time. We're protected from the radiation, we're protected from the rocks, and those little domes, they're looking at little mobile hospitals, basically. How can we help humanity survive while they're out there? Astronauts, they're not going to be able to be good at every single thing, so we're going to have to send up stuff that can help them make dressings, make medicines, and various other things. All that work is going on in there. And then here, this research is all about sustainability. So we've got a big push going on at the moment to look at how we can create energy from solar energy, from wind energy, from waves and various other things. This is looking at how we can store that. So at the moment, when we create energy with a wind turbine, if it's not used straight away, it can get stored in batteries, but there's only so many batteries you can build, and they're not very sustainable in themselves. So this is looking at creating caverns in the salt so that we can fill it full of compressed gas, compressed air, probably to start off with. And as we create that energy through that wind or that solar, we'll compress that gas and hold it there. And then we can release it later through turbines to recreate that energy to use much later on. So basically, these are big underground batteries, and salt is incredible for that kind of thing because it's often a cap rock that's used for oil and gas wells and various other things. And as well as that, we also have seismology here, just like they do in Australia, so we can monitor earthquakes. And you think about earthquakes, you think about the big tectonic shifts, the stuff that happens. Sorry, excuse me, I'm full of cold. That sends, massive earthquakes, but there's lots of small little earthquakes that are happening all the time that we don't feel them because they're so small, but these incredibly sensitive sensors can pick these things up all the time. Just little shifts under the sea and all kinds of things. So we have thousands of kilometers of roadway down underground here that are kind of like a spider's web network. So we can make a really nice map and triangulate where these things are coming from. So it's a really incredible place. I'm not sure how I'm doing on time. I'm kind of rushing.
You've got about 10, 15 seconds, and then we'll ask you some questions, Emma.
Okay. Well, I'm just going to stop there because I have never done better on time. So thank you very much. Happy to take questions with Clara, and I think Johnny and Beth will be around as well. So if anyone's got any questions, fire away.
Perfect. So I'm going to ask you a question straight away that we asked to the supple team. What qualifications should you have to work at Boulby, and do you offer internships?
Great question. Great question. And the answer to that is not a simple one. Clara's with me, particle physicist, doctor, PhD. I don't have a PhD. I run the facilities operations and outreach. So to run a lab like this, it takes an incredible team of engineers, technicians, scientists, and people who care for the lab. So we've got clean room technicians who are running around. You might have seen them in the background. Beth has just finished an apprenticeship. Johnny came in as an industrial placement student. That's someone who kind of does work experience as part of their degree. And then we kept him because he's brilliant, as you can see. And so there's a whole range of careers from engineering, like say technical. We have business administration people, accounts people. It takes a whole massive team to make something like this run. And again, it takes the physicists, the scientists to be able to kind of drive us forward and know what we're looking for, know, the directions we need to take, but they couldn't do what they need to do without a team like us who kept the space open for them, kept it usable, kept things running. And like I said, the engineers who actually build stuff, you couldn't get very far without them.
Yeah, physicists come in all flavors. So some of us have a bit of hands-on experience, but some people are more on the theory and the calculation. So you need people who can actually run a lab and work with the equipment. So it takes all kinds of people.
Fantastic. So my next question is, looking at all of you, I can see that you are all wearing different color hats.
Oh.
And I also noticed this will be a question we can ask the Supple team when we get to the part with all the people. But you weren't wearing any hats. Could you tell me a little bit more about why you're wearing hard hats and what the different colors mean, please?
Sure, I'll let one of these guys take that.
I can get us started if you'd like. We can all talk about our hats in turn, maybe. So today I'm wearing this orange hat because when we're inside of our lab in our main hall laboratory space, Beth mentioned earlier, we operate this as a class 10,000 clean room. So this is a really clean environment. So when we're out in the tunnels, we wear either green or red hats, which Emma will tell you about in a second, but they're all dusty and they're dirty because they've been in the mine. And we don't want to bring all that dust and dirt into this very clean space. So I have changed my red hat for an orange hat because this orange hat is cleaner. So I don't bring dust into this space.
Okay, I'll go next. So Johnny's saying his orange hat is cleaner, but it's not clean enough for bugs. Being in the main lab, there is quite very low dust levels, but it's just not low enough for bugs. So we have specific hats that are only for this room, and we have to change a lot of our other PPE too, to make sure we're not bringing in any contamination from the main lab into here.
Thanks, Beth. So as you can see, Clara and I are outside. I have a red hat on, Clara has a green hat on. These are our dirty hats, as we would call them. This means that they've been in the mine. And the difference is my red hat means that I'm a supervisor, and that means that I've had specialist training so that I can bring other people underground and I know what to do in case there was an emergency, or if anything happened down here, I've got all of the necessary training. Anyone who hasn't got all of that training is a visitor or a user. They wear a green hat, and that tells people that if something happened, they should run to the red hats. They will deal with everything, and anyone who's got a green hat on just needs a little bit extra care and attention.
Fantastic. And I think we've got one final question before we ask everybody some questions. And I think it's going to be for Clara. The question says, at the LHC, is possible supersymmetry the only dark matter candidate that Atlas, etc., are or could look for?
So it's a great question. Supersymmetry is a really excellent theory that proposes a whole new set of particles. What we really like in particle physics is to change one of the parameters, and then that often doubles our particles. And it's a beautiful theory that, if it were true, one of the lighter versions of these new particles could have been an excellent dark matter candidate. But we have been looking for it for many, many years in our experiment, and we've been able to rule it out in a lot of different scenarios. So it's not completely excluded. It could still be a possibility, but it's becoming slightly less likely with our experiment. And so we like to keep our options open, and we search for lots of different theories in our experiments. And also what we're doing a lot of now is we've been doing machine learning work for 15, 20 years. But we also do, thanks very much. We also do anomaly detection, which is a machine learning method where we learn the data that we have in the Large Hadron Collider, and we can see what we expect to be in that data. And if dark matter is something unexpected, then it will show up as an anomaly in our measurement. So this is what we call a model agnostic search tool, because we're not arrogant enough to think that we're perfect and we've come up with all of the options. So we try to just see if there's anything weird in our data. And then if something like that showed up, we could see how it's interacting in our experiments at CERN. And then we tell everybody else, hey, look, we've seen this kind of weird anomaly in our data. Have you seen it in your experiments? And then this is where the collaboration comes in, and all of the experiments around the world can look for that as well. So there's lots of different theories. So far, we haven't seen anything that we can get excited about in that sense for dark matter, but we are still searching, and it takes many years to do these kind of precision measurements.
Fantastic. Thank you so much. So I can see that our supple team have come to join us. And I have a question that says, so in terms of scientists, is it more physicists who work on dark matter research or astrophysicists as well? So Si, I'm going to hand straight over to you to answer that to begin with.
Yeah, that's a really interesting question, and it does make sense that given that all the evidence for dark matter is astrophysical in nature, it does make sense for astrophysicists to sort of build simulations and things so that they can study possible models of dark matter, and that's in fact what happens. So, for example, the group here at the University of Melbourne, we're predominantly focused on this WIMP dark matter detection, but with the Center of Excellence of Dark Matter, we have other collaborators who are primarily focused on astrophysical candidates for dark matter as well. Yes, so to answer your question, you do have astrophysicists, and their involvement is profound in this. I hope that answers your question. Would anyone else like to chime in?
Fantastic. So my question is still about, just to go back to the hats thing. So at Boulby, they have to wear their hard hats because they are in a working mine and they wear the same clothes that the miners wear. But I can see that you are wearing slightly varying shades of orange and yellow and no hard hats. Can you tell me a little bit more about what you have to wear to go underground?
Absolutely. So exactly like the guys at Boulby, when we are outside in the mine environment, we have a really different situation because we're absolutely controlled by the mine outside. And we put on our hard hats and our miners' belts and gloves and make sure that we've got everything that we need to go underground in exactly the same way that the guys at Boulby do. We also always wear our high-vis clothing. Si is in yellow today because he's just got a different type of high-vis clothing on, but this is generally our uniform for going underground in. And inside the supple facility, we've just conducted a risk assessment for the wearing of of those hard hats inside the facility, and we have agreed with the mine, obviously, because we work very closely in conjunction with our mine here, that they're not required inside this facility.
Amazing. That answers the question perfectly. So we pretty much are coming up to the very, very end of our webinar today, but we have had so many amazing questions coming in. So I think we will try and get some answers out on those as we go on with the webinar, but we will bring it to a close for now. So I'm going to just make it sure we can see everybody. I'm sure we can. The Boulby team appear to have had a slight power cut, so they are all in the dark now, but their Wi-Fi is still working, so hooray. That is great. And I am going to pop in the chat some links so that you can see if you want to find out more about the work that everybody is doing. Those are in the chat for you now. But I just want to say a massive thank you to Stawell Underground Lab, Stawell Underground Physics Laboratory, the Boulby Underground Lab, and Particle Clara, and all of the fantastic people that we've got here today. It's been amazing to have you. And those of you that have joined us, thank you so, so much. Good night to those of you that are in Australia, and almost lunchtime for us in the UK. So I hope you all have a wonderful rest of the day, and we will see you again soon. Thank you so much for joining us. Goodbye.
Bye.
Thank you, everybody. Goodbye.
Bye.
Thanks all.